So this chapter will conclude part one, which is all about these tabular methods. Now, the important thing about tabular methods is that the problem is small enough that we can enumerate all of the states or all of the state action pairs, ideally, and use that however we want to solve the environment. So typically we would, save estimates or try to compute estimates of the state values or the state action values, and then, you know, use that to our advantage. Now, in this case, we are talking about enhancing previous learning methods with, something we're going to call a model, which is going to look very similar to the value estimates, but it'll be obvious when we get to this. So this first part sort of reviews a lot of what we started with, if you recall, which is the dynamic programming chapter, in which case we had this full probability transition function for the environment. And with this, we can, do these dynamic programming techniques, or we sweep through the state space and we try to, we can just directly compute the optimal value function. And then from that, we can get the optimal policy. But then later on, we introduced environments where we don't actually have this function. And instead, what we have is the ability to sample from it. So we may have an environment where we can input a state action pair and observe the transition. And for those environments, we had other techniques to use, like the sampling techniques, like Monte Carlo. And then in some cases, there's sort of something in between. So, what we're going to do in this chapter, the beginning of it is we consider deterministic environments. So in a deterministic environment, this transition function will just identify which transitions are possible. But the probabilities in that sense won't really matter, right? Because like every state action pair will have a deterministic transition with probability 1. But then what's useful about this will be sort of telling you which transitions happen. Like, so it's more like a lookup from state action to state reward. Now, if we have a deterministic environment, you might imagine that like once we observe a transition and we know that it's deterministic, then we sort of have a piece of this, just from observation. And the idea behind the model we're going to build is that we're going to save the transitions that we observe. And because if we're told the environment is deterministic, we know that whatever transition we observe, it's going to happen that way every time. And we're sort of guaranteed to have a piece of this. And then we can sort of combine the techniques from before where we can use the model or the partial model we have to do updates, prior to receiving new interactions with the environment. And that was the big difference between the dynamic programming techniques and the sampling techniques, is that in dynamic programming, we observe, this function, we have it, and then we can just compute the value function from it. We don't need to interact with the environment. We just need to evaluate this function, unless it depends on what you consider interacting with the environment. But let's say, like, traditionally, if we have the ability to sample this function, that would be like some black box environment where we can observe a transition. And in that case, every time we observe the transition, that's like an interaction with the environment. Whereas anytime we sort of use what we think this function is to compute stuff, That is a different computation, which we could take advantage of, but it wouldn't be considered like an environment interaction in the same way. And maybe it's cheaper, like especially if this is just a lookup table, this may be a lot cheaper to just query than to actually, get a transition. In the case of like a real environment, like a robot or like something physical object, that may be very slow and costly to query. So the idea here is that we're going to introduce this sort of planning concept where previously we would like observe or simulate things, and then we would do updates from the result of the simulation. But now we're going to add, there's sort of this opportunity to do additional updates through the planning process. And depending on the technique we're using, the planning will look different. So here there's sort of this is the general picture for the techniques in the chapter, but here, the model is going to be whatever we're building from experience, like some kind of, I said, if it's a deterministic environment, it could be some kind of lookup table. Then the simulated experience is like, this is where we actually sample from the environment. And this, where we could imagine, could be a more costly process. And then, we're going to collect the values from that and do something with it, probably update the model and the value estimates we have. And then ultimately, like the policy is always derived from the value estimates, just like before. And a lot of times the actual update we do with the model or with the values, like it's gonna all look the same. It's just that the source of the target, the update target, is gonna change, whether we're doing sort of a planning step or more traditional learning. So the first example of this is like the most basic planning algorithm that you could do. So this is called, and in this case, most of these techniques early on, we're going to focus on these sort of one-step tabular methods. Remember, these were methods where we're using bootstrapping to update the action values based on the transition states. And this update looks, like the update we had in Q learning from before. So the actual like update is the same. The main difference here is that we're gonna sort of very explicitly sample, transitions from the environment. And because this is the tabular case, we have a finite, and countable, like a manageable state space and action space. And in this technique, we just pick a state, pick an action completely at random. And we're really just using this step to add to our model. So like whatever the model is, I actually send it to us and obtain. Wait a second. I'm sorry. Now I'm confused about this algorithm. So I think yeah, select the state in action, use the model, whatever. So this I guess hasn't defined what the model is. Oh, I know. I'm sorry. This pseudocode is showing the planning part. This will fit into a larger algorithm. So this is like, let's say we have some model. It hasn't been specified yet how the model is built, but we have some environment model that we can basically ask it what we can sample from it instead of sampling from the true environment. But this update step is basically just doing Q learning on the reward and state transition that we get out of the model. Yeah. And then, it's assuming that like the model has the ability to give us the answer for certain state action pairs. and we're just going to randomly go through them. This is like just sweeping through the state space. And you could also do this without the model, like with the actual environment itself. But in the past, this sort of technique would involve having a trajectory that we go through, and then we do Q learning on that. Versus it may be kind of inefficient to like actually just do random samples every time. But nonetheless, this is sort of what the planning phase will look like. So, okay, so the first algorithm that actually like combines this with previous techniques is called DynaQ, and I'm trying to think, why is it called DynaQ? Dyna, I think, just means dynamic, but this sort of block diagram shows that what we're trying to build, just like in the previous cases, the value function and then the policy derived from the value function. Now that will sort of direct how we act in the environment, just like before, where we have these, we're going to sort of have episodes, or in a continuous task, we're going to have, some state we're keeping track of that we keep transitioning through the environment. And if we sort of act in the environment and have some trajectory, and then we look at the transitions and we do updates, whether it's, the SARSA updates or Q-learning updates, that would fall into the category of all the techniques in the previous chapters, where we're just learning directly from experience. Now, the alternative is that we take, some amount of experience, and we use that to build a model, which you'll see exactly what that model looks like with DynaQ. And then we can update the value function in the policy somewhat, using the model. And the model's derived from experience. So it's just a question of how we're using the experience. And it's going to end up providing a little bit more flexibility by decoupling the number of update steps we can do with the actual physical steps that we're taking in the environment. But, the actual technique we end up using could be a combination of this, where we decide how much of the experience we want to apply directly and how much we want to use to build up the model. And, it's not like there's a single answer to this, depending on the environment and whether it's deterministic or how big the state space is. It may be beneficial to try to plan on a model, or it may be beneficial to just learn directly. But I don't know, are there any questions about this sort of basic diagram picture, or maybe it'd be helpful to actually look at a more concrete example with DynaQ? So I can move on to that if there's no questions about the distinction between direct reinforcement learning and model learning and planning. Okay, well, so for DynaQ, actually, I didn't read here. Yeah, I mean, DynaQ, just like we saw before, will end up using sort of Q learning style updates, but with the addition of this planning phase. So what do we mean by the model in DynaQ? So first of all, we're considering the case of having a deterministic environment, which means that for a given state action pair, there's a defined transition that happens with a single answer. So you get a certain reward and a single state. So when we collect, real data from the environment, what ends up happening is we observe a transition. And then in our model will just be a lookup table. And the lookup table will have a list of all of the state action pairs that we have attempted and what they led to in terms of, what the reward and transition state is. So that's it. We just, at some point in the process, we'll have a lookup table. The lookup table over time will hopefully, build up with all of the relevant state action pairs. But early on in the process, it may just have, one or two state action pairs in it. And even though we're actually sampling from the environment with real transitions, in between those samples, we have the option to use this Q planning algorithm where we do the Q learning updates, but we do them from the model that we have so far. So we've observed a certain number of transitions. And I mean, another way of thinking about this is sort of given the limited data we have so far, we're just sort of converging Q learning more to what, I mean, potentially all the way to what the optimal policy would be, given the limited data that we have. And this sort of makes the technique more akin to what we had before in like generalized policy iteration, where, we could choose to take any piece of the process to convergence early on. Whereas like typically we're collecting data from the environment and we're not expecting our value function to converge, or we don't want it to converge because we want to keep making use of new data. And we're sort of bringing the value function closer to convergence as we're collecting new data rather than forcing it to converge with a limited amount of data. And if sampling from the environment doesn't have any cost, if it's free and it's fast, then there's no, there may not be much of a point in, doing more update steps without collecting more data. Because like if you're going to do another update step and collecting the data is cheap, you might as well, do the update with more data. Because we know that as we collect an infinite amount of data, eventually we're guaranteed to converge to the true optimal value function. Whereas if we have a limited amount of data, then even if we try to progress that to convergence, it's not going to necessarily, be the correct value function because we don't have like a full picture of the environment. So this is sort of a diagram of, part of this diagram incorporates what the DynaQ agent does. But, so the real experience, we're sort of using it in two different ways. We're using it in sort of one step maybe to update the value function. And then we're also using it to update the model. And then with the model, we can do these planning updates. And, we can also use the real experience to do direct updates. So this is the pseudocode for DynaQ. So I have it in here, a version of it where I have these lookup. I mean, the way I did the lookup table is a little different and it might be more optimal if you have like a small enough environment. But the most straightforward way is just to have like a dictionary lookup where you have these state action pairs and they map to a reward in a state transition. So we can see that, if you take out the planning, this will look just like, one-step tabular Q learning, where we start, we're in some state, we're following the epsilon greedy policy with respect to the current value estimates. We take an action, observe the transition, and then this is the Q update, where we're doing an expected update where, this should converge to the optimal value function. in the limit of, infinite samples and of the learning rate, decaying with appropriate properties. So, this should look familiar. This is just the Q learning update. And normally we would do one step of this every time we get a transition. Now, this is where there's this added thing. So if you were to have a 0 n, this would just be Q learning. But now we're going to keep track of one additional thing here, which is the model. And here the model is just this lookup table, which will keep track of transitions we've actually seen. And then once we have the model, we're going to do these same Q learning updates, but by just randomly looking at transitions we've already seen. So if we only have like 2 transitions that we've seen, and we're looping for whatever 10 steps or something, we're just going to do with the same learning rate a number of these updates. So these planning steps just reinforce, some of these learning steps that we would have already observed from real transitions. So, it may seem like, in a sense, we're just like repeating the Q update multiple times, but the difference is that we're not just repeating this state action pair Q update a bunch of times. We're gonna, once we've seen a lot of these, we're gonna randomly sample, different ones that we've seen. So at every step, we're gonna potentially learn from all of the previous experience, not just the immediate step that we just took. So anyway, it looks very similar to Q learning. We have this. And I get like the real question is, what, if any, is there a benefit to doing this? Like even in a case where, here, like hopefully the model is very cheap to access. There may be cases where taking the action is slow. And that's a case where maybe this technique would converge faster under some assumption of how slow this is. Another question is like, assuming that there's not really any disadvantage to taking actions, like maybe it's just as fast as querying the model. Another question is like, well, in that case, is there any advantage to doing this planning? Like, why not just, observe more transitions from the environment and not even bother with this? So, those are questions that we can attempt to answer with different examples. So, the first example they have is this maze. And the maze, we just have these simple, rook style actions. We can only move, in each of these 4 directions. And the maze, it has some obstruction to it, but still, the optimal path is not that difficult to find. In this case, I think it's a 14 step path to the goal, going around these obstacles. And you always start here. This is always the goal. And this is structured as a task, which again, depending on how you form the maze task, this is structured where you only get a reward of 1 at the goal. And then they use discounting to incentivize, the agent to finish the maze. The other way of doing this, which you saw before, was having a reward of -1 on every transition. And that, I think, like a lot of the techniques that are introduced to address problems of sparse rewards use this maze task with just a goal reward. But a lot of those problems, a lot of these techniques will work better if you have a reward of -1 on each transition, because then you eliminate the problem of having very sparse rewards, which with n-step learning, where we saw like there's some balance of n where you want to propagate the goal reward back, through the model. So anyway, because we're trying to make this, basically makes the task more difficult, just having this goal reward. We also have to like take a specific value of gamma, which may affect the problem, but in this case, I think for this style of task, any gamma less than 1 should produce the same optimal policy, because there's no like there's no like failure case here. Like what we want to finish, if we don't hit the goal, we'll just keep spending more time in the task. So
I guess, that makes sense, given that, there's no failure state, like the example previously where, there was a cliff, essentially, the goal being on one side and the third state being at the other side.
well, I mean, even in the cliff maze, like you were placed back at the start and just got a large negative reward. So, I guess this would be very different if you had like a failure state here instead of the goal, where it's like if you got to that state, you got a large negative reward and you just ended the episode, and that was it. And that was like a failure and you didn't get a chance to restart. I mean, it depends on the task, but I believe it's not explained that thoroughly in the book, but if you have a gamma, like if you have a task like this where there's some like failure state and you have a gamma, this obviously incentivizes you to finish the task quickly. And I don't think it should be a problem for the maze, but like, let's say there's a way to finish the maze really quickly, but there's some small probability of that path like failing and leading to the failure state. Like you'd have to make a different kind of maze for that to be the case.
I guess, depending on, the state of it, it might, try to, depending on how the rewards are structured, it might try to, might possibly try to go to the failure state as quickly as possible, because going to the failure state is faster than going to the actual goal state. For example, like, if the square that's nearest to S was the failure state.
Well, yeah, I mean, well, you have to make the failure state like costly, like but yeah, I mean, maybe it just gives you a reward of 0. So, you get a goal of 1 if you get to the goal. But if you set a specific value of gamma in that situation, you are deciding like what the trade-off is between failure. Like, because there's a specific um like number of steps where like if you could finish this fast, that is worth it given a certain percent chance of failure. So in that case, like the gamma. Now, in the case of a simple maze like this, you can always guarantee avoiding the failure state. So there's no trade-off to be had. But you could change the environment so that like there was some square, like, okay, I give an example. I could like make this example later, but you could have like a maze where there is a short path to the goal. And the short path, the square right before the goal, or like, there's some chance, like a 1% chance from that square that you like get sent to the failure state instead of getting to the goal. And then there's like a path that's twice as long, but there's 0 chance of that happening. Right? So, which path is optimal in that case would actually depend on the value of gamma that you pick. Because, it depends on the balance between the shorter path and the probability of failure. But then I'm trying to think, so if you have the same task and you structure it so that you get a reward of -1 every step, and the failure state, yeah, I don't know. In that case, it might be the same kind of trade-off actually. In that case, you'd have to decide if you want the failure state to, how much of a negative reward do you want it to give? Because like if it just gives you another reward of -1 versus reaching the goal would give you a reward of 0. But either like however you structure the problem, you just have to remember like if you have tasks where there's like a terminal transition, which is some kind of failure, depending on how you structure gamma or all the rewards, you are like explicitly saying how much failure are you willing to tolerate in exchange for, a bigger success. So, and this kind of thing could apply to games too, where it's like if you're playing chess or some game and you're like, well, there's a path where you'll win like very quickly, but there's like a 1% chance of losing. Is that worth it to you compared to like a guaranteed win that takes, an enormous amount of time? Of course, like and there's some tasks where you don't want to tolerate any failure, which would be more straightforward. But, in that case, like if you're doing a game task, for example, the simplest way to avoid that problem is just to not use a discount rate, in which case, you're just saying the only thing that matters is winning. The speed to the victory doesn't matter at all. As soon as you put a speed to the victory, but there's a chance of losing, then there is some like path to victory that is so short that you're incentivizing it to take that even if there's a small chance of losing, because you're putting that much benefit on winning quickly. So I think, that's why practically most of these agents that are trained to like win at a game will not actually care about how fast the victory comes, because you could always end up, introducing that, that trade-off where it may try to take a risky path to a faster win, even though, you don't really want it to lose, but you sort of then have to deal with the fact that all wins are going to be treated equally. But in the case of the maze, because we do want it to actually finish the maze, I mean, the problem with the maze task also is that you could just bounce around and never finish. At least if you're playing a game like chess, you have to make a move. Like there's no option to not move. So you will, always progress the game forward. And until you get later on, like in the end game, where you actually can have just both players shuffle their pieces back and forth and not, not do anything. But luckily, like the game environment itself has a finite limit on the number of moves you can make. So that protects you there. A game like Go is that's actually not possible because you always have to place a tile and eventually the board will be filled up and there won't be possible to move anymore. So anyway, we have this maze task where we do have a discount rate. So we are incentivizing the agent to finish the maze as fast as possible. There is no failure case. So we just have this goal where we get a reward of 1. And if n is 0 in the DynaQ, we're just doing Q learning from before. And this is now showing, how fast the agent is finishing the maze for each episode with, however many planning steps there are. And of course, it's not surprising that as we add more planning steps, we can find the optimal policy in fewer episodes. But that's also because, I mean, if we add more planning steps, we're doing more of these queue updates, right? So like this isn't normalized to like the number of updates. This is showing per episode. So we would always expect, hopefully, I mean, there's something really wrong if this isn't working, that, adding more planning steps and effectively more queue updates. Now, what this is showing, though, is that if the maze, like, if it really was slow to run the maze, the actual maze, then, like, the planning steps might be fast, and this might actually converge faster. In the case of, how we're setting this up probably, doing a transition in the
But
maze is going to be a similar cost to actually querying the lookup table.
wouldn't the balance of the inner loop and the episode loop basically essentially boil down to having a similar amount of computations?
Well, I mean, so this and this are going to be the same. So whether we do more updates here or we do them as planning steps, we still have to do these updates. The thing that might take a different amount of time is, in this case, we're doing updates based on the transition here, taking the action in the maze. In the planning phase, we get the transition from the model. And the model in this case is only previous transitions.
I guess
So
that
this could be
relationship is not
fast.
necessarily like the absolute amount of operations that it would take, but basically have the actual sampling take longer than the planning steps essentially in
Mhm.
real time.
Yeah, so I mean, it really depends on how the implementation works. I mean, if you really want to know what method is faster, you would have to have an idea of how long it takes to do each step. In this case, I wonder if, okay, so here is like, this is like calling the step function on the maze. But it's like, because I have this coded up, like I could, benchmark this and see, although I don't want to have these things. So, but of course, like I've written this maze. So like this depends on how well and how optimized my implementation of the maze is. So this is like 45 nanoseconds. Now the alternative is like, if I have some dictionary, where I have and like this is, going to some, I mean, I can just make all the transitions the same. But like basically your model is going to end up looking like some kind of dictionary like this. In this case, state. Yeah, okay. So I only have four actions here, but like the number of states could be like pretty high. But if I have like, so like if you have implemented the model in this way, then the question really becomes like, how long does it take to query from this dictionary? And that, like, I'm not actually sure, and that also depends on like the programming language you're using. But let's see, if I query like, this thing, although I should do this thing like I did before. But it's probably going to be a similar time, or almost exactly the same. So like, but again, like we're sort of, you have to imagine a case where the maze is something that maybe you have to like physically interact with. And then the maze queries could be extremely slow, like even seconds, versus just querying the lookup we have in the model is going to be, nanoseconds compared to, whole seconds. So, but really like, I guess like another figure that could be in here that I should maybe make a note to make this figure, which is the, I guess, steps per, you would have to sort of equate number of queue updates with how quickly the episodes are. That's part of it. So if the model and the action taking are the same speed, then all that really matters is the number of queue updates in terms of like the cost. But, obviously, if taking the action is slow, then adding more planning steps is sort of free compared to taking more actions. So that's what you have to imagine is like a use for this. So let's see. So in this figure here, so I have an example. So anyway, here's an example of the maze from the chapter where I'm just showing the random policy in the maze. So, you know, just bounces around. These W's represent where the wall states are. And here's the goal. So this is what it looks like with a random agent. And then, you know, this is like, obviously with all these planning steps, you basically solve the maze after, you know, three episodes. So 3 episodes would be, again, 150 plan, or wait, no, way more than 150. I mean, for each step that's taken in the environment, right? So if we do this like for 3 episodes, like if the first episode, you know, or like let's say we like finish the first episode. So we've essentially just like moved randomly in the environment. Then we have all the examples. Now, remember, because this is a deterministic maze, once we've randomly gone through the maze, we almost like have a model of the maze complete. Now, you could imagine at that point just doing dynamic programming on the model, which would also work to solve it. That's another option of planning is like you could actually do the dynamic programming updates with the model. Because remember, since the maze is deterministic, if we just go through the whole maze, the model we have is a true model. Like we will actually, at the end of that, we will have this already. And remember, if we have this, we can just directly solve for the answer. Now, the reason why we're not doing that necessarily is because it's not guaranteed that we have every transition in our model. We may just have a few. Like if you look at this random path through the maze, like I didn't visit this state at all. And depending on the random path, there may be states that were unvisited. So we don't have a complete model. So this is sort of like, you know, similar to doing dynamic programming updates, but it's sort of in between. But, you know, we are using the model to update and we are sort of sweeping through all the states that we have access to at the time. So what this diagram is showing is this is showing the difference in what values have been updated after going through the first episode. So, you know, we've gone through the first episode and now we're starting the second episode. And actually here on my diagram here, this is showing the values that have been updated after the second episode. And but you can change this in here. So this is showing after the first episode, what happens is for n equals 0, this is just tabular Q learning. We've gone through all the states. And in here, we only get a positive reward when we get to the goal. And we only transition to the goal from this one state. So basically, all of these other updates will just keep the value estimate at 0. And then this one state right before the goal transition will be updated with the reward of 1. And with the planning, remember that the model we're building during planning, until we get to the goal, it just has 0 transitions. So the model, as well as, you know, both methods are going to look the same after a single episode. So actually, all of the planning steps that are done in episode 1 are completely worthless because all they're doing is looking at transitions, everything's 0. So after the first episode, both techniques have only updated this single state. Does that make sense? Everyone, like we saw this before with having a goal state and a goal reward.
Yeah, well, that makes sense, given that for the any one-step process, that it would only update the state that's nearest the goal.
Yeah.
Well,
But now, imagine now we start episode 2. Okay. So episode 2 with the tabular Q learning, we now, all the states estimates are 0. This one state has a non-zero estimate. So the agent is going to go through randomly for all of these states. And then when it gets to one of these states, well, in this case, like this state, which is close to this one, it will say, oh, well, there's actually a transition into a state with a positive value, right? So now the state immediately next to this state will get a value update, which will reflect the fact that you can reach this state, which is a positive value. So basically, every episode, we're going to update another state adjacent to a state with a positive value. And eventually, this will propagate back to the start. We saw this before with previous maze tasks. So, right, with one-step tabular learning, this is how the updates propagate. And you would need to have, so see with zero planning, we don't learn the optimal policy until we've gone through like 30 episodes or so, because we're not going to actually find out what to do properly until this is propagated all the way back to the start. And in this case, it takes like 14 steps to do that. If it worked perfectly, we might have the optimal policy after 14 episodes, but practically, there's going to be some ambiguity where to go until we really fill everything in. So I'm just going to show. So does that make sense that on episode 2, the Q learning will just update one additional state? This will also update as well. It'll
yeah,
become
that
even
makes
higher.
sense.
So here, I'm going to click this forward to episode 2. Okay, so now we have another state updated, right? But look at the planning agent. So the planning agent, again, has only experienced 2 episodes, but and it's not perfect, but look at this optimal value function. Like already it's learned that from here you can step across here and up to the goal. So the reason why the planning agent is able to fill in so many more states is because even though only one of the values has been updated, when we do the planning, because we already know the transitions, like we have an example of a path to this state, right? Like there is an example path which has reached this state from the previous episodes. And when we do the Q updates, where we're randomly sampling the states we've seen, during those planning updates, we can propagate this value as far back all the way to the start. Actually, this has already found a path to the goal, right? Like if you follow these arrows around, you already can go like this and get to the goal. This is just after 2 episodes. So this is like can be the power of the planning updates, is that we don't have to, we're making use, the model is basically telling us where we can end up on transitions, but the value estimates are not good. But just from this single positive value estimate, we know that if we do the Q updates enough times, it'll propagate back to the start. In the case of no planning, we have to actually perform that many episodes for that to happen. Because we're only doing a single value update for the states we end up at along the episode trajectory. But in planning, we can just look back through all of the previous things like, well, because basically what the planning agent is doing is it's saying, okay, I know that this state has a positive value from episode 1. But I also know that this state transitions into it from the model, and then this state transitions to this state and this, and it can just, as we do that, it can just feed that back all the way through. So with enough planning steps, what the planning model is doing is basically calculating a dynamic programming solution. I mean, without doing it, with sampling it on the model. And it may not be the perfect optimal solution already, because we may have taken a weird path to the goal. But as we add more episodes, so see, as I click this up and you look at the non-planning agent, you can see that it's just learning a single new transition, which is correct every time. Or, multiple ones. Like in this case, it's, it's back propagating this frontier of, optimal transitions. And it can branch out. Like here, it's already branched out where it's learning this path and this path. But, the planning agent has already, I mean, I would argue that even just after, episode 2, it's already basically learned the optimal policy. The only sense in which it's not optimal is like maybe, it has like a certain blind spot on one of the states it never saw on the first episode. But other than that, it will learn optimal. And this is why the planning is so effective with deterministic environments. It's very important. Remember, like the maze is deterministic, and that's a big reason why this is so useful. Because remember, if the environment is tabular and deterministic, that means that the model we're building is essentially a perfect model. Like it's telling us exactly what the transitions are. And in fact, you could replace the environment with that model. And my code for the environment could just be that lookup table, which might even run faster than computing it. So I think that should basically cover DynaQ, and maybe we talked about it thoroughly enough to think about this exercise, which is the non-planning method looks particularly poor because it's a one-step method using okay, so the question is, this is using one-step learning, right? Like the bootstrapping update here, like in Q learning, right? We're just bootstrapping a single step. But we know there's n-step methods, and in the extreme case, there's Monte Carlo methods, right? In the Monte Carlo method, we would simulate an episode to the goal, like this episode, and then we would perform updates at every state action pair along the path based on how long it took to reach the goal, right? So we know that there is a technique where after one episode, we update all of the visited values. Okay? But this exercise is asking, so let's say we use a multi-step method, like n-step, 10-step, or, Monte Carlo infinite step. Do you think one of the multi-step methods could do as well as the Dyna method? Explain why or why not. So imagine like we do a single episode, right? Monte Carlo. We would update a lot of states, not just one. Okay.
Yeah.
But the question is, would it like in the planning method after episode 2, we know we already have a close to optimal policy. So do you think is it fundamentally different from the n-step methods and the Monte Carlo methods? Or could we just replace this as one of those and also get the same benefit, after like 2 episodes?
Hmm. wasn't, the whole point of like, the DynaQ agent is because the one-step methods are essentially faster, and so if you were having the entire Monte Carlo color computation to the end of the episode, then you already get a path to it, so, well, path from start to finish. So I wouldn't expect the change to be, then wouldn't it basically start conversion rather quickly anyways, without even needing the blinded policy.
Wait, so what? Okay, so imagine if we did the Monte Carlo method, it would do a random episode and it would reach the goal after a lot of steps. Like here, so here's an example of a random episode. Right? So remember that for the Monte Carlo update, every state action pair visited is going to receive a value estimate. That value estimate is going to be, in this case, sort of 0.95 to the power of how long it took to finish from that state. Right? Because it's based on that episode. So we know that for example, like, so the value like around at the start for different, we could have also ended up at the start multiple times, and then taken different actions from it. And we might have wandered around for like 1,000 steps. So like, for example, if you look at the planning agent, like, look, this is after 2 episodes. So, it seems like the planning agent already knows from the starting state that you should go down and over and down and over like this. So like it seems to know the correct actions for states all the way back to the start. But if we do Monte Carlo learning, all these states back here, this episode, if it took like 1,000 steps, all of these transitions are going to be valued as like very low. It's only like when we get to the very end here, because the only option was like to step up, but even like from here, we could have gone down all the way to here and then back up. And we're going to average all that together. So because we're following the random policy, like far away from the goal, even though we've updated all the values, they're all going to be values that look like, well, all these transitions look pretty bad to reach the goal because it took so long because we're just bouncing around randomly.
Well, I guess in that case, because of the discount factor, basically anything that's near the start state would be rather bad, well, low probability values. Well, and so the planning then would still be hopeful.
Well, the same thing would apply if we just have a -1 reward in every transition and it takes like 1,000 steps. All these states would just sort of look like they have a value of like, -1,000, right? Like until we get close to the goal. I guess the main difference with the planning is that we've wandered around randomly. We do one step. So because we're following the random policy, right? Like it's actually not that useful to update all of these states. And remember for the end step learning for different maze tasks, there was some optimal n that was good. And it wasn't Monte Carlo. It was a much lower value. So even though we could update the values all the way back here, from the random policy, it's not going to be that useful. But you could probably see that this value update is very useful because we happen to transition into the goal and we know like, oh yeah, this is actually, a useful update. And then what the planning agent does is it just takes this one useful piece of information combined with all of the knowledge of which states are connected, and then it can fully solve the task with that information. Whereas Monte Carlo, we'll do one step of policy improvement. It's still going to take a large number of episodes before we converge to the optimal policy. And then we could do like a 5-step method. A 5-step method might update like 5 of these values, but it's not gonna do this. It's not gonna update everything back to the start. So this sort of decouples the queue updates from the data collection. And this is a particularly, good example of this working well. But there are reasons not to do this. And that's where what comes into the next section, which is, what if you think you have an accurate model and it's actually not? And that could happen in different situations. This is sort of an artificial situation of this, where you have a maze and then you just swap it out for this other maze. And in this maze, the path to the goal goes to the right. And in this version, you have to go to the left. And actually, if you try to go to the right, you never get anywhere and you get stuck. So what they're showing here is that if you do DynaQ on this very quickly, when this line is straight, it just means that it's found the optimal policy. Every episode is basically taking the same number of time steps according to the slope of this line. Now there's a new slope, right? Once we swap this out, this now takes longer, right? Like this path to the goal is slower to the left. So the slope when it's converged is more shallow, right? But there's this flat period here. So this dotted line represents when we swap out the environment. And once we swap out the environment, then you can see that it goes a lot of time steps without getting any reward. And that's because, right, this is just stepping and getting stuck here in this corner. And it's not until we update all of the stuff that's wrong about the model until we, do this. Because also remember in DynaQ, just like here, how after a little piece of information, we use the model in planning and get what is really just an optimal policy. So if the model is correct, this is very powerful because we can get the optimal policy. If the model is incorrect, then we do all these queue updates with a bad model, and we end up, being very confident at a certain optimal policy, which in this case would be like, ramming into this wall over and over again. And that's why it gets stuck for so long. And there's an even worse case. I mean, you could argue, at least in this case, the model eventually learns. It takes a while, but it corrects itself. And this is showing something that hasn't been quite explained yet, which is there's an alternative to this algorithm where they put in a factor which basically says that the model values are not considered as much the older they are. So if there's some part of the model which hasn't been updated in a very long period of time, then it's just treated as if the reward you get from that transition is actually higher than you think. You just add a value. It just incentivizes the agent visiting states in the environment that haven't been seen by the model in a while. So that's one way of dealing with this. But even if we don't do that, eventually it will correct the model.
But the blocking case is a separate one because basically the entire model starts breaking because of the blocking until it eventually finds a new path. While the other one, that's the shortcut one, there's no incentive at all to basically explore and find the shorter path after a long time.
Yeah, I mean, it's important to note that in the shortcut maze, this path, once we introduce the shortcut, this path, all of the value estimates for this path are going to be accurate, right? The steps to finish the maze are correct. So when this goes through and it uses the model and updates the queue function is converged and it is correct. And every state visited by the agent, it appears as though everything is correct. And that's why it will never actually check this other path to the goal. Now, there could be cases where there's a shortcut opened up, but it also ends up affecting all these other states, and then eventually it would correct the model, probably. But because of how this is constructed, right, following this path to the goal will take the same exact amount of time, even whether or not the shortcut is available. So this is also showing how DynaQ, this slope again means the slope represents the sort of the optimal path, and the slope stays the same after the transition. So it never finds the faster path. Whereas this other agent, which ends up incentivizing visiting actions that haven't been seen in a while. So in this case, if we eventually follow this path to the goal, all the states on the right side are just going to be ignored. And what this other agent does is it just says, okay, like for all the states you've ignored, if you've ignored them for a long enough time, just check them out again. And that's what happens over time. We see here, this is the bonus reward assigned in the other agent, where tau is the time since a state action pair has been visited. So as tau goes to infinity, you're guaranteed to start visiting those states over time. This is just one way of doing it, but this ends up fixing this problem. I mean, it basically fixes every problem you could run into by forcing the model to just be updated, like periodically, with things that haven't been seen in a while. So there are some exercises to think about this. This one is, why did the Dyna agent with exploration bonus perform better in the first phase as well as the second phase of the blocking and shortcut experiments? So we understand that the DynaQ plus is necessary to deal with once we've made this transition. But like, why does DynaQ plus actually do significantly better? I mean, it seems to converge much faster to the optimal policy even before we've switched the environment. In both cases, really, here you see it has a slight edge here. And yeah, we're also, keep in mind that when we follow the actual transitions from the environment, we are following the epsilon greedy policy. So there is still this exploration bonus, regardless, whatever we think the optimal Q function is. So is any idea for why DynaQ plus would do so much better even before we've switched the environment?
Maybe the exploratory state allows it to explore a bit more, perhaps.
Mm-hmm. So remember, this was run. So normally we would just follow epsilon greedy here, and then we're updating the Q function. When we do planning, so in DynaQ plus, the difference is during planning, we use this reward instead of the normal reward. So, but it's basically not trusting the model as much during planning. And then that model is then used to do the, have the agent follow in the actual environment. Oh yeah, here's an example of both mazes. So anyway, I mean, it's unclear exactly what's going on here, but it's possible that this task just would do better with a larger exploration early on. So they picked there's an epsilon of 0.1 used here. And, you know, it's possible that maybe a larger epsilon is just works better in the early phase of the problem. And what this bonus factor does is just sort of boost the value of actions that ordinarily wouldn't be seen as optimal. So I would guess it's just sort of a coincidence that this task, you know, is more favored by more exploration. But here, let's look. This question is a little more interesting, which is if you look at figure 8.5, the difference between DynaQ plus and DynaQ narrows slightly over the first part of the experiment. What is the reason for this? So once these have sort of converged, it appears like DynaQ at this point has converged. It's found the optimal path. It looks like that the DynaQ plus is sort of losing a little ground as we get to the end here. Like there's a gap, and then the gap narrows a little as we get, you know, before we swapped at the environment. So what do you think is the reason why DynaQ plus is losing a little ground on DynaQ early on?
I guess, whenever you have like, any problem that's like, a multi-dimensional space and you're trying to find the optimal optimization function of it, that coefficient, I would think that coefficient of the reward, the k plus times square root of tau, would result in the optimization function not being able to get as optimized.
So like the whole purpose of this is to correct the model for things. But in this part of the task, the model is correct for DynaQ. So what DynaQ plus in this phase of learning is basically testing actions that it thinks might have changed, but the reality is they haven't changed. So it's going to be less optimal than DynaQ, which is just assuming the model is correct. Again, DynaQ will work better if the model is correct, which in this case it is until we get to here. So remember, like if the model doesn't need to be corrected, then this will make things worse. We do this because we're basically we're adding incorrect rewards to our updates, right? These are just to incentivize exploration. Okay. And then here the exploration. So the way DynaQ plus works is during planning, it changes the reward used for the Q updates. But we don't have to do that. What if we do the Q updates the same, and then when we pick the policy, instead of following the epsilon greedy policy, we follow this policy where we pick the action where this is maximal. So we have the Q, and instead of the epsilon exploration, we have this exploration based on the time since the last update. So we are just explicitly forcing a higher probability than usual on action selections that haven't been tried in a while. Question is this better or worse than the method that adjusts the reward during planning?
I
And
guess
for
the
this,
first question that I would have is that would it, violate some term of possible convergence, or would it still converge theoretically?
yeah, that is one question you could ask. So we are changing the policy that we're following. I don't think it will affect the convergence because we're still doing this Q update, and whatever policy we're following, this will still be able to converge. Because Q learning is like, we could even be sampling, like here we're not even following a policy, right? We're just picking random transitions and doing the Q update. So, actually, so I just thought of something with this, which is that if we have states that we have been visiting very frequently, this factor will not actually cause exploration for those states. Whereas the epsilon greedy policy sort of will have this boost from the planning states that aren't visited frequently. But if we're in the area of states where we have seen them a lot and we're doing epsilon greedy, we will take random action sometimes with those. In this case, if tau is 0, then this doesn't give us any bonus exploration. So if we follow this, we could actually still get trapped in something suboptimal, because we're never actually going to explore around the space along the trajectory that we're taking. Right? So like anytime we're visiting states that have been, recently sampled, we're not going to explore. Whereas the epsilon greedy sort of treats all states the same in terms of having an exploration bonus. I'd say that's, I would think, a potential problem with doing it this way. I did show this same task. So this is showing DynaQ plus on the transition task where we swap the environment. And this is showing the version like this, where we don't use the epsilon greedy policy. And it seems, I mean, of course, it depends on the parameters you pick. With these parameters I picked, it seems to be slower at converging on both, both initially and after the transition. Oh, actually, this is interesting. I'm just noticing this now. This is sort of the shortcut example. And it looks like with the shortcut example, oh yeah, I think this actually is like a pretty straightforward answer. Remember, the whole point of DynaQ plus was that in the shortcut example, we need some incentive to visit this path, like even though these values are correct, right? So how do we ever discover this other path? And what I'm noticing now for this alternative method is it has the same problem as DynaQ, right? It never learns the shortcut path. But if you think about if the agent is following what it thinks is already the optimal path, right? All of these states have been visited. Like every state it looks at is visited, has been recently visited because it's along what it thinks is the optimal path. And for this example, because of the way we've structured the exploration, it will never actually test these other states, just like DynaQ won't test them, because the tau here is always going to be a low number. Whereas with DynaQ plus, because we're randomly sampling states from the model, what's going to happen is these states over here are going to appear to be higher value. And then, even though we're following the epsilon greedy policy, eventually these states over here are going to be thought of as being such a high value that they're going to be followed, because the planning updates are going to propagate all the high value stuff all the way back to the start. So I actually think that is the most straightforward answer to the problem with this technique, is that it doesn't actually accomplish the goal for the shortcut maze, where we open up a better path, which the agent is never able to discover. Here, let's look at this final exercise, and then we can stop the end of this section. But how might DynaQ be modified to handle stochastic environments? And how might this modification perform poorly on changing environments is considered? How could the algorithm be modified to handle stochastic environments and changing environments? Now, some of these things will be addressed in techniques later on in the book, but I would say one sort of obvious thing we can do is, instead of just saving the transitions in the model here, what we could do is save a list of them as one option. So we could have, state action pairs. We could have all of the observed transitions, and we could count them up. So have sort of a list of how many times we observe each transition. And then we could use that as the distribution of transitions. And then when we query the model here, we could just sample from that. So like, let's say half the time we've seen this transition and the other half the time we've seen this other one, then we can just use that probability when we get this from the model. So that's one option. It has the same issue of not being able to deal with when the environment changes. We have a problem of like, how do we then correct this model? And one way of correcting it is we could do the same kind of thing that we did for DynaQ Plus, where we add this bonus reward for cases where we haven't seen a transition in a long time. But there is a potential concern with that. Well, one problem is that now we don't have just a single, update where we're adding to the reward value. But I think there's even additional problems. I mean, I think I have to think about it more and maybe look at what happens in some of the later sections. But I think what I had said previously is that when we do need to make a correction to the model, because we have this sort of distribution model now instead of a deterministic model, it may take a lot longer to update the model. When we experience something new. So I mean, we want to end up sampling these transitions, but again, like if we sample a transition, but there's like 5 potential states it could end up in, then we may have only corrected like 1/5 of the model, whereas previously, as soon as we get the new value, it's correct. So I think there's just many more visits we have to make. So the issue is with the previous method, if we visit a state again, then we're setting tau to 0 as soon as we visit the state again. So then we've eliminated the bonus, but the reality is we may need to sample more transitions to update the model. Like especially if we have like some sort of running average of things we've sampled. If we have the deterministic model, as soon as we get a new sample, we replace the value and we're done. If we have a distribution model, we have to keep averages and we don't know if the environment's changed. So we may have to sample another like 100 transitions before we actually, update the model completely. And if we use this method, we can't really do that because, visiting a state once might not be enough to update it. So we have to think of a substantially different way of handling this. And there's probably clues for that later in the chapter, but we can talk about that maybe when we finish some of the other techniques. But I think we can stop for now. I mean, the DynaQ and DynaQ Plus kind of cover most of the basic outline of how planning works. And then the rest of the chapter deals with, ways in which we can improve planning and be even more efficient with how we make use of data we've already collected about the environment. So does that sound good? Any other questions about these first 3 sections? And sounds good to everyone to stop here, and maybe we'll see. We could probably finish the chapter next time. Hopefully. Okay, and also, if anyone, hopefully all the links in the meeting description are sort of complete and give you everything you need, but you can always send me a message if there's a problem with one of the links or with opening the notes. But I think we'll stop here for now, and yeah, thanks for coming, and see you at the next meeting.